Hello. Sorry I'm late. Weather key and Zoom weren't cooperating again. Um, do you see the desktop? Do you hear me by now?
Yes.
Yes.
Okay, thanks. Okay. All right. Today we're going to start talking about window scheduling itself. We're going to start the chapter on scheduling. Now, to give you an example, an idea of what we're going to do, um, we had these. I'm looking for the process and state zip file. There were some programs in there. We're um, just show you real quick, remind you of something. We had these examples of processes that were CPU bound and IO bound. Remember, we could run this program here, and it was a program that used up CPU time. Okay, so this program, compute program. So I would say compute program 64, and it wants a command line argument. Oopsie. Okay, it wants a command line argument. Okay, so I'll give it a command line argument like 10. It runs for 10 seconds. Now, notice that it's bouncing around on different CPUs. Okay, and that's the scheduler. The scheduler. That's one of the things we want to think about. What's happening with the scheduler? Why is this process moving around from CPU to CPU? Now, that's happening. If we go back over here, remember that's happening. The bouncing is happening. Let me get the right picture. Um, in the chapter on process states, where's the book's picture? Oh, I think it's there. That picture there. Okay, the bouncing happens when you go from running to ready. Then you're in the ready queue. When the CPU scheduler is ready to put you on a CPU, sometimes it puts you on a different CPU. Okay, so what's going on between bouncing back and forth? How is the scheduler deciding? For example, another thing is if I run multiple copies of this program here. Okay, if I go back to that folder, I had a version of this program that ran multiple ones. Okay, so this one that says do computes. Okay, it it runs multiple copies of this. Yeah, it runs as many copies as you give it command line arguments. Okay, so what it does is it runs multiple copies of this program here. Okay, so if I run do computes, okay, if I it also wants a command line argument. It wants to know how many. So like a 4 to 5 second job. Okay, now the scheduler is scheduling. There's two processes at least going through this cycle. Okay, so we've got at least, or if I go over here and I do a 30-second job, another 30. So here's three 30-second jobs. Okay, we think of these as tasks for the computer to do. I've given it three tasks. I'm going to run three instances of this program here. Okay, so the computer is has this work to do. It's got to run three instances of this program here. And what it's going to do is it's going to schedule them. Well, actually, what's more interesting is to do this on one CPU. Like right now, okay, the scheduler is allowed to bounce them around between CPUs. Okay, so the scheduler's got these three things to do, but it's also got three CPUs to use. So it's probably, well, it's not actually just saying it's not doing the obvious thing of putting one on CPU one, put one on CPU two, and put one on CPU three. If you notice that they're oops, they're really moving around between CPUs. Okay, this we want to talk about the scheduler making these decisions about that stuff. Now, what's another thing I can do, and this is the way we're going to approach it. We're not going to think about the scheduler having lots of CPUs. We're actually going to think that the scheduler has only one CPU. So most of the theory we build up is if there is just one CPU. Okay, so that would be, and over here I could do that by this program, do computes with affinity. It runs multiple instances, but it puts them all on whatever CPU you tell them to. Okay, so it lets us set the affinity before we start the program that runs all the jobs. Okay, so do compute. Let's see, which one was it? Okay, okay. If I give, like, if I want a 30-second job, a 30-second job, a 30-second. So there's 430. Oh, and then actually, the affinity is the first parameter. So I'm going to put it all on one CPU, CPU one. Okay. If I remember, if I did that, that's CPU two. Or no, I'm sorry, that's CPU two. That, you might think, oh, CPU one, CPU two. Remember, that's hex. That's not CPU three. That's CPUs one and two, because three written in binary is 1 1. Hey, CPU three is 4. That's CPU three. Okay, because this is, remember, this is a hexadecimal number. Okay, and that'll be important later on, because when we write the code to talk to the scheduler, we have to talk to it in hexadecimal. Okay, so there's CPU one. Okay, now I guess, notice that they're all running on the same processor, and now the scheduler is actually having to work harder. The scheduler's got one CPU to run these 4 processes on. You can see how they're running much slower because they're actually sharing that CPU. And so right now, if we think of our picture over here, 3 of them are in the ready queue and only one of them is running at a time. Okay, so we've set up a situation now where we got 4 processes all running on CPU 0. At any given instant, one of them's running and 3 are in the ready queue. Now, they move back and forth in every 40 or 50 milliseconds. So we can't actually like see which one's over here and which ones are over there, because they're moving every 40, 50 milliseconds. But at any given instant, one is running and 3 are sitting in the ready queue. And I had the 4 of them run for 30 seconds each. So to run 4 of them for 30 seconds each is going to take about 2 minutes over here. So this whole thing over here is going to run for approximately 2 minutes. There's the 4 of them. Okay. And you can see they're always running on CPU 0. Each one's got its own process ID number. This one's process ID 10732. This one's 39264. They all have the same affinity mask. They're all told to work on process 1. This guy is like 2 seconds. And notice that right now they're all stepping through their code at about the same pace. In other words, the operating system didn't just say, we'll run one of them till he's done, then we'll run the other one till he's done, then run the other one till he's done. I mean, you could have. When we talk about the theory of scheduling, we'll see that that's got a name. Okay? So right now, the scheduler is basically doing this thing of giving them equal chance at the CPU. So one of them just finished, so the other one should be finishing pretty soon too. Notice that one of them got a little bit more time on the CPU than the others. Yeah, so one of them finished first. They didn't all finish at exactly the same time. So the scheduler did give it seemed that one of them ran a little bit more than the other two because it finished noticeably earlier than the other two. And it took just over, see, it took 2 minutes. Here's the total time. It took 2 minutes and 10 seconds to run 4 30-second jobs on one CPU. The extra 10 seconds was was probably mostly the time taken to do all the switching before, all those context switches. Now remember, that was our other pictures. When you go from ready to running, then running back to ready, you have to do a context switch. Context switch involves a mode switch. The CPU has to go from kernel mode to user mode, from user mode back to kernel mode. And we saw the other day, context switches are very time consuming. We saw that if you did IO, in a wrong way and did too many mode switches between kernel mode and user mode, you could do I/O in an absurdly slow way. You have to pay attention to mode switches. Now, here, every 40 milliseconds, there was a context switch from one process going over here and another one going over here. Over 2 minutes, that was quite a few mode switches. Yeah. So all the mode switching, the decision making of the scheduler, and also just the context switching, the copying the CPU registers into process control blocks. Okay. See, we build up a lot of ideas at this point. When you do a context switch, remember you have to keep we have a lot of pictures. I think pictures are a good way to think about this. But when you do a context switch, we had a picture to kind of make us think about context switches. See if I remember where it is. When you do a context switch, when you switch from him to him, you have to take all his CPU registers and copy them into the process control block. Then you have to go down here and take his process control block and copy them into his CPU registers. Modern CPUs have dozens and dozens. Some modern CPUs have like 100 or so registers. So copying all these registers into here, then copying all these registers into here is time consuming. Not to mention the amount of time it takes to do the mode switch from a user mode to kernel mode, then from kernel mode back to user mode. Okay. So you can kind of get a sense of where this other extra 10 seconds goes. Okay. It's going to go, it's all the overhead. And it's not that bad. Out of 2 minutes worth of work, there was 2 minutes is 120 seconds, and there was about a 10-second overhead. So, maybe I don't know if that's a rough. I actually don't know if that's a rough rule of thumb. It sounds too much. 10% overhead for the scheduler actually sounds like too much. I don't think it's really that much. I think there's something else. Some of that other 10 seconds might have been the fact that the computer's doing Zoom at the same time. It may have been running Zoom on CPU. Remember, we were running on CPU, the first CPU actually zero. Maybe the computer was actually sharing that CPU with Zoom too. So maybe it wasn't just our four processes using that one CPU. Because right now that looks like about a 10% overhead. Because for 2 minutes is 120 seconds, and it was 9 seconds of overhead. Yeah, to me that sounds too much. I don't think a scheduler is 10% of your CPU time. Probably more like 1%. I have a feeling it's much closer to 1 or 2%, but I might be wrong. I don't remember reading lately. I can't remember what the rough rule of thumb is for how much time the scheduler is using itself. I really don't think it's 10%. So I think that other overhead was that the CPU is actually being shared by other things on the computer at the same time. Okay, so it wasn't just our four processes running on that one CPU. They were probably sharing that CPU. Okay, now, so that's now the thing was, how did the operating system decide? Yeah, if there's three processes over here in the ready queue and one running, when he runs out of his time and you have to pick one of these, how do you pick? Now, in this example, there wasn't much difference between any of them. They all looked exactly alike. So you might say, well, what's the big deal? But we think about this, we'll see that they don't have to all look alike. Okay. They For example, one thing I'm not doing yet is I call up Task Manager. Let me bring up Task Manager. We saw in Task Manager that you can set the affinity. Remember, you could set the affinity here. I'm not going to play around with Chrome, but I could set Chrome's affinity. Another thing you could do is set something called the priority. Okay. And we'll see how those processes could have different priority levels, and that could affect who gets the CPU. Again, I'm not going to muck around with Chrome's priority, but there's a whole bunch of different priorities, and you can give different CPUs different priorities. Now, right now, uh, there's a column here showing you priority. Okay. Notice that these guys are part of the operating system and they don't even have a priority. See, some of these are really core parts of the operating system. They don't even have a high priority. Then there's some other parts of the operating system that have a high priority. These guys are all part of the operating system. And then there's some stuff. Oh, Chrome gave itself above normal priority. Okay. That's probably the Chrome process that's in charge of the other Chrome. I would bet. No, maybe not. That might be the GPU process. Yes, it is. That's the one that's talking to the GPU. Okay. That's the that's the process in Chrome that's responsible for communicating with the GPU, for example, for watching videos and if you're running a game in a browser and you're talking to the GPU. So that one got a slightly higher priority. We'll see what that can mean. But eventually it should mean that the scheduler kind of turns to those things first. Notice there's not too many that are set themselves above normal. Um, then you have lots at normal, which seems normal. And then there's below normal, parts of the operating system that aren't very important. And then there's even some things, oh, even parts of Chrome run at low priority. Oh, Chrome's very cooperative. Yeah. My guess is those are tabs that haven't been opened lately. Those are probably tab. Oh, actually, I'm logged into this machine as 2 users right now, so I bet those are Chrome tabs from my other login that are dormant, essentially, because 'cause I'm not logged in, I'm currently logged in on as 2 users, but one of the accounts is it's not the current desktop, so it's just kinda dormant. So I wouldn't be surprised if these are tabs from that other Chrome that've been kinda put into a low priority. Um, I don't Google Crash Handler, Google Crash Handler. Okay, so I don't even know what some of this stuff is here. So there's some things running at low priority. Not too many. No, it's not too many at low, not too many at high, and an awful lot at what we would call normal priority. Okay, so the scheduler should somehow be taking that kind of thing into consideration. Now, I didn't play around uh, with, we were able to set the priority. We were able to over here in this thing, we were able to I wrote it so we could set the affinity. And I haven't sat down and see if I don't know if you can set the priority at the command line. That would make a nice experiment to run these things not only with the affinity set, but also run some with the priority set. Like, what would it look like if we ran one of these with high priority and three of them with a normal priority? We would probably see a difference in how they got scheduled. I'd have to read to see if I'm not sure if you can do that from the command line. Probably can. The fact that you can do it from Task Manager, the fact that you can go in here in the Task Manager and set the affinity and set the priority means I think you can do it from the command line also. Okay. In fact, the whenever I'm interested in knowing what you can do from the Windows command line, I've linked to this before, but there's a I was hoping I'd get them for yeah, here it is. This website here. This website is really good for reading about CMD. It's the single best that I found reference on CMD, better than Microsoft stuff. Okay. This is a really good website for learning about CMD. It's a pretty encyclopedic reference to everything you can do on the command line. And actually, I Googled priority. Let's see if it said, see, start. Oh, here it is. I can set the priority. Okay. So when I use the start command, now start command is what we also use to set the affinity. See, so I can set the start command. If we go back over here, the ones that have set affinity, I was using the start command to set the affinity. Okay, so I got that out of this website. You're not likely to find that kind of that stuff is on Microsoft's website, but Microsoft's a little bit notorious for not having a particularly user-friendly documentation. They document their functions really well. So create process, read file. When you want to read about a Microsoft function, they're really good at documenting that. Very, very good. But when you want to read about CMD and a lot of other things too, no, they're not very good. So this one's a way better documentation for CMD, but for their functions, they're the best place to look up documentation. and the data structures that go along with the functions, startup information data structure, process information data structure. But CMD and quite a few other things like PowerShell. PowerShell, there's probably a gazillion better websites for reading about PowerShell than Microsoft stuff. So here's a, so the start command, later on, maybe I can do some examples where we actually not only set the affinity of the processes that we launch, but we can set the priority of them also. And then we would see that the scheduler is it should give a priority to the processes that have a higher priority. Now, what that would mean in terms of over here, in terms of a picture, whoops, is that the process with higher priority should spend more time in the running state. When it's time to choose a ready process, the one with higher priority should be the one that usually gets chosen. Okay. Now, we'll see later on that that doesn't mean that you always choose the process with higher priority. Because if you do that, you get something called starvation. You can end up with lower priority jobs that never get a chance to run on the CPU, which is considered a bad thing. You don't want processes to never get a chance to run. So even when you have priority, we're going to see that the scheduling algorithms can be pretty sophisticated. So you don't just say, oh, higher priority comes first. At some point, the operating system says, but this low priority one has been sitting here too long. So now this low priority one is going to get its turn, even if there's a high priority one. Something's called priority boost. Okay, so we'll see various things like that. We'll talk about we're going to talk about all the scheduling algorithm in all its details. Okay, so this is just to give us a sense of what it is we want to do. We want to understand how the operating system is choosing who to pull out of the ready queue and put in running. And we're going to emphasize it as if there was just one CPU. Okay, for a long time. Actually, I think all of the textbook theory on scheduling is, what do you think? No, if you here's chapter 10 on multi-CPU scheduling, and we're actually not going to look at it. Okay, we don't have time to do that chapter, so we're going to do the single CPU scheduling, which gives you a really good sense of what's going on. The multi-CPU scheduling is actually pretty complicated. So if you really just want to understand the basics of how an operating system works, you don't really need to read about multi-CPU scheduling. So that's where the textbook talks about what if you're scheduling 8 CPUs or something like that. Turns out that it's useful for someone who really cares about the details of operating system, but 90% of what you want to know is in the stuff on single CPU scheduling, which is these two chapters here. That's what 7 and 8 is what we're going to cover. We're going to cover chapters 7 and 8. Multi-level feedback queue is what Windows does. So chapter 7 is going to be scheduling in a really what seems like silly way. You're going to wonder like why this is useful. And then chapter 8 is how Windows and Linux really schedule. But you would never understand chapter 8 if you didn't read chapter 7. Even though chapter 7 is going to seem silly, and you'll see why when in a minute. It's going to seem like it's silly, like it wouldn't have anything to do with a computer. Turns out that the key idea in the multi-level feedback queue scheduler is buried in here. Yeah, and if you didn't do the silly stuff, you'd have a really hard time understanding why the current modern algorithm, you have a real hard time understanding why it's structured the way it is. Okay, so one chapter of silly scheduling, and then a chapter of modern CPU scheduling of one CPU. And this lottery scheduling, I don't even know who uses it. The book has this chapter on lottery scheduling. I don't even know if it's interesting, but I don't know if anybody uses it or not. And then there's this chapter on multi-level scheduling, which is tricky. And I don't think it's really necessary to study it. We'll jump into the virtual memory space. After we do chapter 7 and 8, we'll jump to chapter 13. We'll skip the multi-CPU scheduling. Okay. All right. So let's talk now about the actual. Oh, I've got a zip file here that's got some more information that's specific to Windows. In fact, if you download this zip file, it reproduces the folder, the stuff we were just doing. I put this folder on CPU bound versus IO bound in both of those zip files because it's kind of a nice. These examples are good for thinking about this. So this Windows scheduling folder, it's got this same subfolder, CPU bound versus IO bound. Okay, so because it's just those examples are good for thinking about scheduling. Here's a folder that we'll look at later on multi-level feedback queue. That's when we get to that chapter. That folder will be about that chapter. We'll talk a little bit about the fact that elevators have a lot to say about CPU scheduling. Yeah, we'll see that thinking about what you do with an elevator in a skyscraping building is got a lot to do with how you might think about CPUs. So elevator scheduling ends up being kind of a cute example of how to think about scheduling. So how to think about scheduling, there's a little bit of motivation that comes from thinking about elevators. Okay. And then here's a folder of where you can read about Windows. I put links to, remember I showed you those books that are out there. You know, if you want to read now, it's not the whole book. This is just they make available a couple chapters of the book. So, but I put links to the couple chapters that are out there. So if this is what you can read for free out of those books. And luckily, the chapter on scheduling is chapter 5. Well, it's chapter 5 in the older edition, the 5th edition, and it's oh, it's also chapter 5. It states chapter 5 in both editions. Okay, in it's chapter 5 in both editions. See, 5th edition and 6th edition. And there's currently this current edition is I think the 6th edition. And now this is actually really useful. If you see, if you there's chapter 5 on process threads and jobs. People use the word jobs on computers pretty often. We think of a process to do as a job. Okay, so people use the word process, threads, and jobs. We're not going to talk much about threads. We're going to talk mostly about processes, but they use the word jobs as the CPU's got a job to do, and that's what processes and threads are. And then, that was the 6th edition. And then there's a little bit, here's what it was like in the previous edition. It's kind of, it's interesting. It's not only interesting to read this stuff, especially if you really want to understand Windows, it's also interesting to see how they change from one version of Windows to another. So this was, there's, actually there's less change to Windows is there more change to how they described it. They rewrote this chapter because it's hard stuff to talk about. This chapter is long and pretty complicated. So they kind of rewrote it to try to find what they thought was a better way to explain it because not that much changed in Windows, but they changed the way they describe it quite a bit. Okay. So there are little technical differences. So here, like this picture changed a lot from there to there. Okay. If you want to be an expert in Windows, like if you go eventually get a job where you're really working with low level stuff, servers, web servers, database servers, your cloud systems, this and this kind of stuff really matters. You can be a real expert at this level. After taking a class like this, you can turn to this book and then learn the real nitty gritty of how Windows implements the theory that we learned from our textbook. Okay, so I put links to those in this folder. Okay, okay. And these here are just, I thought they were cute. These are people's PowerPoints from all over the place. I found some. Oh, I'm double clicking on the PDF file and it's opening, I think, on a different window. Yeah, it opened over in another window on my other monitor. Okay, these are just, I thought, really good PowerPoints. If you like, so they're good examples in here. They're just more things to read. Okay, uh, I just thought they were kind of good. I found a use reading these PowerPoint slides. Besides, well, some of them are PowerPoints that are based on the book we're using. Some of them are just PowerPoints that were based on other textbooks. They cover all the same ideas, and I think they're good summaries. There's just a bunch of them. I thought these were really good ones I found on the internet. So we'll see that we're going to do a lot of these kinds of examples here. We're going to start talking about these kinds of examples. They're in our textbook also. First come, first serve, shortest job first, response time, round robin. These are the ideas we're going to talk about. So these PowerPoints are kind of, if you can just glance through them. Uh, right now it might be a little bit early, but after we've talked a little bit more, or after you read the chapter in the book, you might find some of these kind of interesting, that different people summarizing CPU scheduling in different ways. I think there's like 5 or 6 of them in here. Okay. Okay. All right. So now let's start actually talking about what's in the book. What's the CPU scheduling that's in the book? Okay. Um, what we're going to start with is basically a, it's not even CPU scheduling. Think in terms of, you're at the grocery store and everybody's got a shopping cart and they're lined up. Suppose there's only one cashier. Okay. Okay. So the problem is, what's the best way to let people check out? There's a bunch of people with shopping carts. There's one cashier, and what would be the best way to let people check out? Okay. So there's first, like, one strategy is you let them get in a line. That's called, we have a name for that. It's called first come, first serve. Okay. And actually, let me open the textbook to the chapter we're talking about. Okay. First in, first out. First come, first serve. First come, first serve. Okay, that's one of the algorithms. You let people get in line. Okay. But if you think about it, a lot of grocery stores have another checkout line, the one for 15 items or less. Okay. Why do they do that? Well, over here, we have a name for that. That's called shortest job first. Okay. What does it do? What's the point of having, in this case now, there they do 2 checkout lines. In our case, shortest job first isn't really 2 checkout lines, but it's the same idea. If you have 3 people waiting in line and 2 people have big shopping cart and one person has a pack of gum, if the person with the pack of gum is at the end of the 2 people with big shopping carts, the person gets kind of annoyed. It just seems weird that they have to wait for 2 big shopping carts to be done. What's happening is that their, what we call response time, is very bad. The amount of time it takes them to get service is really slow. On your hand, if you let them jump to the head of the line, it actually wouldn't affect the other 2 people at all. Now, in a real grocery store, they'll grumble. But if you think about it, if you let the person with the 1 pack of gum jump in front of the other 2 people, they'd be out in about 10 seconds, and it really wouldn't affected anybody else's response time. Okay. So you would be better off letting short jobs jump ahead. Now, grocery stores aren't going to let short jobs jump ahead, so they create a separate line for the short jobs. But its goal is to what we over here would call response time. Let's see. Somewhere in here, they define something called response time. So what we're doing is we're trying to make something better for people. Okay, we have this, we have something we measure called response time, and we'd like to have the average response time be as good as possible. Okay, now here, let me draw a picture and show you. We're gonna do a lot of things with timelines and pictures here. Okay, here's here's how I'm gonna think about things. I'm gonna think of a job as that's a job. It's a certain length of time. And here's another job. I'll use a different color. So I'm going to have 3 jobs, and they're going to be 3. Oops. Okay. Think of 3 jobs. Okay. How can I order them? Now I'm going to run them. So on a CPU, I would run them by ordering them in a different way. So for example, I would see if I can draw this well. I might run the red. Yeah. Run the red one, then run the. Ah, I don't actually. Let's see. I'm not used to how the, okay, there. Then you would run the green one, and then you would run the blue one. This is one ordering of them. Okay. Now, on the other hand, you could do a different order. You could run the green one, the shorter one first, and then you could run the red one next. Now, this is what a scheduler does. Scheduler would be doing this thing of choosing what order to put them in. Okay. And then I'll say I'll run the blue one last. Okay. Now, what difference would this make? Okay. The green one's going to be happier because his average turnaround, the turnaround, what we call the turnaround for him was better here. Okay. The turnaround for him was better because he was, here he had to wait, and then here he didn't have to wait. The red one may or may not care that much because he didn't have to. Imagine if this green one's a little bit shorter than this. The red one maybe waited a little longer in this one than it did in this one, but it didn't notice as much. And the blue one, it's the same either way, whether you did the red one first or the green one first. Okay. Each one of these jobs, think of these is something to do, something to do, something to do. You can schedule them this way, or you can schedule them this way. Okay. Each job has a bunch of parameters. For example, it's got what we call its turnaround time and its response time. Okay. The turnaround time is the time from when okay, we're going to assume that all these people got in line at the same time. So at time 0, they got in line. So we'll make this thing here time 0. So they arrive at time 0. So if I can think of them as saying at time 0, they all arrive. Now later on, we'll say, what if he got in line, he arrived first, and then a few minutes later, then he arrived. So that would be a different problem. Right now, we're going to assume that there's 3 things to be done, and this one takes this much time, this one takes this much time, and this one takes this much time. So you can imagine 3 shopping carts arrive at the checkout counter at exactly the same time. Okay. But then the question is, maybe we imagine there's a scheduler at the shopping cart line, at the checkout line, who says you go. And some stores do that. Some stores actually will tell people you go first, you go next. Okay, they might actually put a scheduler there. Okay, so this would be one scheduling. This would be another scheduling. For a given scheduling, each job has what we would call, for example, a response time. Another one they have is a turnaround time. Okay. I think, let's see. So, and they also have their completion time. Their completion time is how much work they have to do. How much time does it take to complete them? So this one has got a longer completion time than this one. This one's got a longer completion time than either of them. The turnaround time is the time from when they arrived to when they're done. So in this schedule, the turnaround time for the red one is to here. The turnaround time for the green one is to here. From here to here is his turnaround time. And for the blue one, the turnaround time is from here to here. Okay. And over in this one, in this schedule, the green one's turnaround time is from here to here. The red one's turnaround time is from here to here, because we assume that they all arrived at time 0. Okay. So in this schedule, red's got a better turnaround time. And in this schedule, green's got a better turnaround time by a lot. Between the two of them, red's turnaround time is not that, especially if we imagine if I drawn green as really short, you'd say that red's turnaround time didn't really change that much between these two schedules, but green's turnaround time changed a lot. Response time is the amount of time it takes them to get going. How long is it before somebody responds to them? The response time of the red one is 0. He arrived at time 0 and he was scheduled at time 0. So his response time was 0. The green one's response time was the red time. Completion time is what green one's response time was. So response time is how long from when you arrived to when you start working. Okay. Turnaround time is from when you arrived to when you finished working. So the blue one has the same both response time and turnaround time in these two schedules. Okay. So the processes come with their completion time, and then depending on how they're scheduled, they could have different response and turnaround times. Okay. A scheduler is trying to mostly optimize between these response times and these turnaround times. Okay. You want the average response time to be as good as possible. You want the average turnaround time to be as good as possible. Okay. And so later on, we'll do actual calculations and we'll see which one of these schedules, like there's several different schedules you can give these three. Like, for example, the worst schedule you could give these from almost everybody's point of view would have been to do the blue one first. Oops. For example, if you did the, uh, um, for example, the worst thing to do would be to do the blue one first, followed by the red one, and then do the green one last. That would actually be about the worst thing you could do because you'd make about everybody as unhappy as possible. The blue one probably wouldn't care, especially if you exaggerate this. If the blue one's really long, the red one's kind of in the middle, and the green one's really short. So if you imagine this as very long, medium long, very short, this would the difference between this one and this one actually wouldn't affect the blue one a whole lot. Okay. But the red one is affected a lot and the green one's affected a real lot. In a sense, this is the optimal schedule and this is the worst schedule. Okay. And we're going to see that what this schedule is doing is just doing shortest job first. This one's actually called shortest job first. If you do the short jobs first, you get what's called good turnaround time. This will have the best turnaround time. The average turnaround time of this one will be best. The average turnaround time of this one will be the worst. It'll be very high. You made things a little bit better for the blue one, but not much better. But you made things a lot worse for the red and really a lot worse for the green. On the other hand, if you turn it around, blue's not that much worse off than if it was over here. Red is considerably better off, and green is way better off than it was over here. Okay, so these are different schedules for these jobs. So we think of these guys over here as jobs. So we refer to these as jobs. Okay, they're jobs to schedule. Okay, so these are jobs. We have 3 jobs to schedule, and then we can put them on we imagine that we have one CPU, so we can't do green and blue at the same time. That would start talking about having multiple CPUs. We're going to always assume that there's one CPU. So if I want to make sure that, so I'll say this is our only CPU, CPU 0. That's one, and this is similarly, this is still our only CPU. So this is a different schedule of our only CPU. Okay, and this is a third possible schedule for our one CPU. Okay, okay. And then what we're going to do is we're going to say, okay, of these 3 schedules, how are we going to decide which one's better? Okay, and what we'll do is we'll say, well, let's choose one of these, what we call metrics. So these over here are what are called metrics. Oops. Things you can measure. Okay, something you can measure. We'll decide what metric is important to us. Response time, turnaround time. Now, completion time is actually not a metric. I probably should. Completion time is the jobs come with that. They come with that's a parameter of the job. So completion time is a parameter of the job. So actually, let me erase it from here because it's not a metric. Okay. So response time and turnaround time are 2 metrics. Now, a job, okay, let me go back over here. What is a job comes with certain parameters. Jobs come with parameters. So for example, completion time would be a parameter of a job. Each job has got a completion time or work time. Okay. Another parameter that jobs have is their arrival time. Another parameter they could have is their priority. So we'll see, we'll have a bunch of different parameters that we could have. So here's an example. Each job will have, now right now, each job I said has the same arrival time. So I'm imagining that all three arrived at the same time, and I have to choose which one to do first, which one to do second, which one to do third. Okay. So I have jobs. The jobs have parameters. The parameters we'll be looking at a lot are how much work the job has to do, when did it arrive, does it have a priority assigned to it? Does, right now I didn't, priority actually come a little bit later. At first, we'll just talk about, in fact, at first, we're not even going to, at the beginning, we won't have any priority. At the beginning, our arrival time is always going to be everyone arrives at the same time. And we're only going to really worry about, for a while, completion time. That'll be our only parameter. This is what I mean, like I said earlier, we're going to do really baby scheduling algorithms. And you're going to wonder, like, why are we doing such baby scheduling algorithms? Because we're giving these algorithms, we're doing scheduling with super simplistics, but we only have one CPU. We're not going to look at priority. We're not going to look at arrival time. We're only going to look at the amount of the amount of time each process takes. But we're going to still see that there's a lot to talk about. So jobs have parameters, and then we have these things called metrics, things that we can measure. The two most important are response time and turnaround time. Okay. And we want a schedule that optimizes one or more of our metrics. We maybe one metric is really super important to us, response time. Response time is how long someone waits until they get started. No, it doesn't, it's not measuring how long it takes them to work. It's saying response time just says, when did you get started? How long did you wait? Did you have to wait till the system responded to you? Turnaround time is what people tend to think is more important. How long did you wait until you were done? Okay, from the time you arrive. So turnaround time is from the arrival time to completion time, to when you're done. Response time is from arrival time to when you start. Okay, those are metrics. Usually we care about the average of these things. Like, here, okay, his response time is 0. And here, his response time is 0. And here, his response time is 0. Well, of course, there's always somebody with a 0 response time. What's more important here is what's the average response time between the blue, the red, and the green. Over here, what's the average response time? Over here, what's the average response time? Or what's the average turnaround time? The turnaround time for him is up to here. The turnaround time for the red is up to here. And the turnaround time for the green is all the way up to here. Compute those three, those are three turnaround times, compute their average. This will have a much larger turnaround time than this one will. This one will have the shortest turnaround time. You'll be averaging 3 smaller numbers than you would be here. Okay, so we're usually interested in the average of these things. Okay, so a schedule is a way of choosing jobs based on some parameters that tries to optimize some metric. Okay, it's an algorithm that chooses the order of jobs based on the parameters of the jobs and some metric that we want to optimize. Okay, let me save that before I lose it. Now, in that zip file that I downloaded a little while ago, this Windows scheduling zip file, I put, there's a file in here called notes that summarizes this thing. So this is how we're going to start. We're going to think of scheduling as we're going to make assumptions about our jobs, and we're going to set what parameters the jobs can have. Okay, so in terms of this picture, what we'll do is we'll play a game where we're going to choose different sets of parameters. That's this thing. We'll make assumptions and set parameters. So we'll say things like, oh, all our jobs arrive at the same time. That's a parameter. All the jobs have the same arrival time. All the jobs have the same priority, but they have different completion times. Okay, that's a choice of assumptions and parameters. Okay, And then here are some parameters. Job duration time, like how long does each job take? Do you know that? Okay. Uh, Later on, we'll see, can jobs be preempted or not? Uh, are you allowed, like think about a grocery store. If somebody's got a huge order and they're in the middle of checking out and somebody comes up behind them with a stick of gum, is the cashier allowed to stop this order, check out the check of gum, and then continue this order? The answer in grocery stores is no. Even though it probably, I don't even know if their cash registers are even set up to do that. Can you pause someone who's being checked out? But the grocery stores tend not to do that. But it would actually be kind of efficient. You know, so in our case, we call that preemption. We'll have a name for that. Can jobs be preempted? And in the grocery store, the answer is pretty much. I've never seen a grocery store that would do. They might be able to. They may. I don't even. I've never been a cashier, so I don't know if you can, if you could just like halt the middle, like just kind of pause checking out one person, check out a stick of gum, and then continue on with this. Now, in terms of CPU scheduling, that's an important thing. If you've got this really long running job and something important comes up that's short, you might just halt this thing. In terms of our pictures, that would be the scheduler deciding to move somebody. Oh, I closed that window. Remember, that would be somebody's running on the. Let me get the picture again. You got somebody running here with, and then somebody arrives in the ready queue that's short and has high priority. So then the scheduler can just put running into ready, put ready into running, let the short job run, and then switch them back again. Scheduler could do that. Yeah. So from from the point of view of computing scheduling, it's going to turn out to be actually pretty straightforward to let somebody in. If a short job comes in the if in so now we're allowing different arrival times. So that would be saying, oh, the arrival time can vary. So while one job is running, another job could arrive. And if that job that arrives is very short, you could decide to interrupt the long running job. Or if the job that arrives is high priority, you could decide to interrupt the job that's running. Okay, so we call those preemption. Okay, those are our assumptions. An assumption would be things like all the jobs arrive at once. That's a trivial assumption. Okay, another assumption is that, oh, you can interrupt a job or not. That's called preemption. Okay, another assumption is, we'll see a assumption the book makes at one point that's kind of dumb, is that all jobs take the same amount of time. The book actually makes this. I think that's actually the first assumption they make. And if you look at the chapter in the book, the first assumption they say is, well, let's suppose that all jobs take the same amount of time. That's an assumption. That's a really useless assumption. And he kind of wastes a couple paragraphs, I think, talking about the case of all the jobs taking the same amount of time. Okay. But that's an example of an assumption you can make, that you can assume that all the jobs take the same amount of time. Okay. Some jobs are more important than others. That's priority. So the first thing is you choose what parameters you have. Are all the jobs the same? Completion time. Do you have a mixture of short jobs and long jobs, or do you have like you could have an assumption could be that you only have long running jobs, not all the same time, but they're all long. Like, all jobs take 15 or more minutes. Okay, that'd be an assumption. Or you could assume that the jobs are all possible running times. So you have a mixture of very short and very long times. You can make assumption about arrival time. You could assume, oh, all the jobs arrive at the same time. We know how much. Now, an example of that would be scheduling truck drivers at the beginning of a day. You know all the work that needs to be done during the day. You know all the deliveries that need to be done. All the deliveries arrived overnight. So that's an example of a scheduling job where arrival time is all the jobs are there by morning, and then you schedule them out in trucks. So you could assume that the arrival time is everything arrives at the same time. Or you could assume that things just arrive randomly, like a grocery store checkout line. Okay, that's an assumption. You can make an assumption about priority. Do all the jobs have the same priority, or are some of them more important than others? Okay, so This is a list of the different things that we in computer programming, in operating systems, think of as the assumptions that we might make. Okay. Do we know ahead of time how much work there is to do? Okay. Now, that's actually kind of weird thing. If I open Microsoft Word on my computer, so I start up Word, I can do that. How long is Word going to run? Well, it kind of depends on how much time I want to spend typing. I don't know ahead of time how long Word is going to run because the computer I'm working on is an interactive computer. But in the real business world, it's actually a lot of programs that are run, you know exactly how long they take to run. It's not like you open up Word and then you sit there and think for a while, then you type for a while, then you think for a while. In a lot of environments, the job you run would be do today's inventories updates. So every evening, a large store might run a program that updates their inventory. They write once a month, they might write a program that does their payroll. Those jobs tend to be, they know exactly how long they take to run because they run them, like the inventory job is run every night, has been for years, and they know that it takes 2 hours for it to run. It's actually not unusual for people to know exactly how long their jobs will run for. Another example is scientific computing, like in the supercomputers in West Lafayette and major research universities. Professors run programs to do simulations on the supercomputers. They usually know how long their programs will run. With not to the second, but to the minute. They might say this program takes about 15 minutes to run. This other one takes 2 hours to run. It's actually not unreasonable to say that you know or don't know how long the job completion times are ahead of time. So every job might come with its completion time. The job arrives with its completion time. Most supercomputers work that way. In fact, most supercomputers, if you ever, you probably never use one, but when you use a supercomputer, you're actually told when you submit your job to the supercomputer to tell the supercomputer how long your job's going to take. They want to know, is it a 1 hour calculation, a 15-minute calculation, a 2-minute calculation? So your program arrives with a completion time, at least an estimate of the completion time. Okay. So on a desktop computer like this, we don't know completion times. Somebody launches Word and you don't know, or somebody launches Chrome and you don't have a sense of how long is the Chrome program going to run. But in a business environment, or in another example might be in certain cloud environments, it's actually not that unusual to know what the duration time is for a process because you kind of know what the process is doing. It's going to process a certain amount of, it's going to update a database, and you know that it never takes more than, you know that on average it always updates the database in 5 minutes. Okay, all right. What's the distribution of the job arrival times? Like, do you know that all your jobs tend to be 15 minutes or more? Or do you know that they just can be anything? I get 1 second jobs and 10-hour jobs. Do you know something about the distribution of the the amount of work to do? Okay. What about the arrival times? What do you know about the arrival times? Are you assuming that's like scheduling truck deliveries where everything is there by morning and you just have to schedule the day's work? Or is it more like Windows where I just decide at some point to run a program? Do you know anything about the arrival times? Can jobs be preempted? Are you allowed to interrupt? If somebody's checking out a big order at the grocery store and somebody comes up with a stick of gum, can you interrupt the big order to check out the stick of gum or not? Okay. Can you preempt job? Once a job is now, notice that on in a computer here, you don't think twice about me launching Word. But when I launch Word, I'm probably preempting some other program that might be running. Okay. On the other hand, if you think about a grocery store, if you're checking out somebody, you have to stop the middle of the checkout to check out somebody else. If you only have one checkout lane, you're either going to let people finish checking out or you have to interrupt them. In the world of scheduling, that's called preemption. And one of the main questions to ask is, are you allowing preemption or not? Okay. In general theory of scheduling, you have to make a decision. Do you allow, for example, very short jobs to jump in and preempt a long running job. Or another possibility is, do you allow a very high priority job to preempt a lower priority job? If somebody important comes into the store, it doesn't matter how big their order is, are they allowed to cut in line? Are they allowed to, are they allowed to, like, cutting in line is one way of preempting. Another way of preempting is actually stopping somebody in the middle of checking out, letting somebody else check out, then going back to the person checking out. So there's multiple notions of preemption. Like if you think in a grocery store, you could let somebody important cut in line, but then there's still going to be, then they kind of cut in line and get here, but they still have to wait for the person who's checking out to finish checking out. On your hand, you could let somebody come up and actually tell the cashier, stop processing the order you're working on, ring up my stick of gum, and then continue back on with the one you were running. So there's multiple notions of preemption. So you have to decide. This is under assumptions. You decide, can you preempt or not preempt? What kind of preemption do you mean? Do you mean letting somebody cut in line, or do you mean actually interrupting a job in the middle of its being done? Okay. Priority. Are some jobs more important than others? Okay. Now, here's another one that's going to be kind of important. This one doesn't have an analogy with the checkout line. Does a job need more than one resource? Like here, there's only one resource, the CPU or the cashier. Okay. Now, on a computer, there could be other resources. For example, what if two processes also want to use the GPU? Like, how does that affect the way you schedule them? Or another example is printing. Suppose there's two programs that want to print. You can't have them simultaneously be printing. So there might be issues with scheduling that have to do with the fact that they're actually trying to use more than one resource. Okay. Uh, so that'll be later on. We'll see. That's actually a real important. That makes things quite a bit trickier. But it's the idea would be that there's something besides the CPU that's being scheduled. So when a process is running, in the middle of running, it might say, oh, and I need the printer now. Or, oh, and I need the GPU now. Or I need to write to the hard drive right now. That's actually our other, in our case, the other resources will tend to be IO devices. Okay. So what do you do when someone needs another resource? That that's tied together. Like a lot of times what you do is, for example, suppose two jobs want to use the printer. They can't use the printer at the same time. One of them is going to have to wait for the printer. Okay. So in a sense, there's that ties in with the preemption and things like that. For example, if somebody has to wait for the printer, do you let somebody else take their turn while they're waiting for the printer? Or does the computer, or is the process that's waiting for the printer actually still hold the CPU while it's waiting for the printer to finish printing what it's printing? Okay, those are actually tough decisions. So the printer might be printing up like a 100-page document. This process wants to print a 10-page document. It may actually have to stop and wait for the printer to be done. While it's stopped, do you preempt it? Do you let somebody else run on the CPU? Or do you let the CPU just wait for the printer to be done, and then you continue on with the CPU job? Turns out that's not an easy decision. Okay, we'll see. When the CPU is waiting for an IO device, most of the time you would just make the CPU preempt so if this guy decided he wanted to use the hard drive, we've said that what pretty much happens is when you want to use the hard drive, you get blocked. So in terms of our other picture, if you decide, that's an example of using another process, you want to use the hard drive. Okay, I forgot where the picture was. So you would, if you want to use the hard drive, you get blocked, and then when you're blocked, somebody else gets to use the CPU. But it turns out that even in a modern operating system, sometimes, even when you want to do IO, it's actually faster to let the CPU just sit there and wait than it is to block someone. That's usually a matter of like waiting for, not for a disk drive, but if you're waiting like for the network card or the GPU, because they're much faster than the hard drive. It's actually sometimes overall more efficient to just let the CPU wait a little bit until the GPU becomes ready, because the context switch of putting is when you interrupt the CPU from one job and you context switch to another job, that takes so much time that it might be less time consuming to wait for the GPU to be ready. Okay. Turns out some devices, even though they're busy, it doesn't take very long for them to get what they need done. So like the GPU might be busy, but it might be faster to wait for the GPU to complete than it would be to context switch to put a process to sleep and wake up another process. Okay. In that case, if it's better to make the CPU wait for the IO device than to put someone to sleep, we say that the CPU spins. Okay, there's this notion of a spins. Yeah, there's even there's something called a spin lock. The idea is a spin lock is where you say to the CPU, just sit there in a tight little loop and wait for a little while. Okay, you simply wait in a little loop, spin. Okay, the idea is that sometimes it's actually better to make the CPU waste CPU cycles for a millisecond than it is to spend 3 milliseconds putting a process to sleep and waking up another process. Okay, so there's this notion of spin locks of sometimes that you would when you want to share another resource, when this CPU wants another resource and another resource isn't available, you wait for it to become available and you just let the CPU sit there and wait. Now, if it's a hard drive, you're not going to let the CPU wait for the hard drive to become available because that takes way too long. So then you would preempt. But if you know that the wait for the other resource is very short, you might spin. So instead of waiting, you might spin. Okay. So this issue of other resources brings up some really tricky issues. The decision between spinning and waiting turns out to be kind of a subtle aspect of it affects a lot the performance of servers. Uh, these spin locks, a lot of research goes into them, like when should they be used? Because the idea that, oh, we'll waste CPU time doing nothing is kind of controversial. But it's not hard to show that in some situations you're better off letting the CPU do nothing for a very short period of time than it is to try to, because it takes so much time to unschedule, to preempt somebody takes too much work. You have to think of it if think about it, the checkout line. Suppose you had to unschedule somebody in the checkout line. So you tell them, oh, you have to take all the stuff that's still on the belt, put it back in your cart, get out of line, let somebody else step in. Then after I process them, you put all your stuff back on the cart. That's kind of what a context switch is on a computer. A context switch on a computer is almost to the point where you're telling somebody, unload all your stuff off the cart. Remember, that would be put all your CPU registers in your process control block. Then when it's time for you to run again, you have to take all your stuff out of the process control block and put it back in the CPU. That would be like telling somebody, okay, I've checked out some of your stuff. There's still some stuff on the belt. Put it all in your cart. Go, wait over there. Then when I finish doing this other person, you can come back and put your stuff on the belt. Okay, that kind of interruption is so time consuming that you might be better off spinning. There's a lot of analogies in CPU scheduling with things like shopping carts, which we'll actually use. We'll use a shopping cart analogy pretty often to think about scheduling because it kind of helps bring out some of these ideas. Okay, so scheduling is about making these assumptions. Okay, now then the other thing is you choose the metrics. You decide what your parameters are. That you decide what these parameters are. Then you decide what metrics you're interested in. Okay, turnaround time and response time are the two most important metrics. Another metric is waiting time. Waiting time is how much time you waited until it's very well. Waiting time would seem to be the same thing as response time. Response time is how much time you waited until you got started. But what wait time takes into effect is what if you're allowing things to be interrupted? What if you allow preemption and interruption? Then if you allow preemption, you could have wait time, which is part of when you got preempted. Okay. So these times can interfere, depending. So wait time would be the same as response time if you didn't have preemption. because then once you get started, like once you start checking out, you didn't wait any longer. The response time would be until you start checking out, and the wait time would be until you start checking out. But if you were allowed to be preempted while you're checking out, and you could be, your checkout is kind of stopped, somebody else is checked out. Well, while they're checking out somebody else, you're waiting. So if you allow interruption and preemption, your wait time can be different than your response time. Okay. So now waiting pretty much only comes into play if you allow interruption. Okay. Yeah. Because if once you start someone, you finish them, then their only waiting is the response time, how much time they waited to get started. Okay. Total completion time, again, total completion time is from the start to when you're done. Okay. I called it here total turnaround time. Uh, Total completion time, another word for that is turnaround time. I should have put that in parentheses because the book itself sometimes uses the word completion time and sometimes uses the word turnaround time. How long did it take you to turn around? It's a weird word, turnaround time, but the phrase, how the turnaround time is from your time you arrive to you can turn around and leave, so to speak. So it's how long you had to wait. It's the total amount of time you spent from the time you arrive to the time you leave. Total completion time. Okay. Another metric we're going to talk about is CPU utilization time. If you allow preemption, you know, well, no, no, that comes in. I'm sorry, that comes into play when you have multiple resources. When you have multiple resources, you could be spending some time on the CPU and some time on the printer, and then there's this question of is the CPU, how much is the CPU being used? If you pause the CPU and it spins while you wait for something, that's not utilizing the CPU. So the CPU utilization is kind of boiled up with, are there other resources? If there's no other resources, then you only use the CPU, and CPU utilization is 100%. But if there are other resources, you may sometimes not use the CPU while you use one of the other resources. Okay, that would be spinning the CPU. Now, on the other hand, you may also just say every time you use another resource, you schedule the CPU on something else. So then the CPU utilization is 100%. Okay. All right. Oh, last thing, fairness, starvation. Remember, I told you that when you have priority, you have to worry. If you have like two levels of priority, and you have a line, and there's almost always somebody, if higher priority keeps showing up, the low priority people may never get their chance. So even if you have two levels of priority, but if half the world has one priority and the other half has the other priority, and you pretty much always have somebody with the higher priority in line, the low priority will get starved. That won't be fair. So if you allow priority, you have to worry about fairness and starvation. You can't let the higher priority monopolize the resource. So that's a metric you worry about. This fairness metric. Are you allowing, if you have priority, are you letting the CPU be hogged up by the higher priority? Okay. Then there's going to be, these are the algorithms we'll start talking about. First come, first serve, shortest job first, longest job first, round robin. So we're going to start talking about those algorithms. Okay. So we'll quit there. So this summarizes what the whole chapter is about. And this is a slightly different way of summarizing it than what the textbook does. I mean, this is actually putting everything that's in the chapter in one list. Okay. Assumptions, metrics, algorithms. Okay. And then the last step is analyze. Like, given your assumptions and your metrics, and given your assumptions and the algorithm you choose, how good are your metrics? That's what it boils down to. You chose an algorithm, you made some assumptions, now measure your metrics. That's the analyze step. Okay. You've chosen an algorithm, you've chosen your assumptions, you measure your metrics, and you analyze, and then you decide whether that was a good algorithm or not, for example. Okay. All right. So what we'll do actually, spring break is next week, so we won't meet again for a while. When we come back, we'll actually put numbers into these pictures like this. We're going to do a bunch of examples with pictures like this with numbers, and we'll start doing calculations like average turnaround time, average wait time, average response time. and we'll do different scheduling algorithms, make these measurements, and kind of see how things work. Get a feel for what these metrics do, what these algorithms do to these metrics, how these algorithms affect these metrics with different assumptions. So we'll do actual calculations. Okay. All right. So have a nice spring break. Okay. Okay. So have a nice, okay.
Professor, do we have homework?
Um, there's one almost ready. I didn't know whether to put it up there since spring break is next week. I could put it up there. I have to decide when it'll be due. Like it's almost ready. See, yeah, it's not. Oh, I see. I did put it. I forgot. I put that up there, and I didn't put the homework assignment up there. Yeah, it's almost ready. I haven't decided when it'll be due. Let's see. I put down March 29th. Uh, that's no, that's too soon. We'll see. So next week's spring break. Okay, that'll probably don't be due March 29th, but I'll try to put it up there as soon as I can. I've almost got it finished. Yeah. So then, but I'll make it due, well after spring break. So yeah, if you want to take a break, you can take a break during spring break. Okay. So yeah, I think that I'll put the assignment up there as soon as I can, but it'll be due, well after spring break. Okay. Other questions?
And our exam is
Thank you,
still
Professor.
March 31st, right?
Yeah. Uh-huh. Yeah. So the exam. Oh, and if you have questions about those exam problems, over spring break, if you want to ask, let's see, where was it? Yeah. Yeah. The exam will be, like it says here, the exam is going to be on March 31st. So that's 3 weeks from now. Okay. So that's 3 weeks from now. Okay. So the exam will be 3 weeks from now. Okay. So if you have questions about these, if you're looking at it over spring break, feel free to send me an email and ask questions about them. Yeah, I'll try to answer the question as much as I can. But feel free to ask questions if you're looking at this over spring break. But yeah, the exam will be exam will be 3 weeks from today. Okay. Other questions? Okay. So look for the homework assignment. Yeah, I'll try to put it up there in the next day or two. I'm almost done writing it up. So, like I say, it won't be due until probably right after the exam. I'll make it due. I'll decide. I'll have to decide when will be a good due date for it. Okay. Other questions? Okay. Well, have a nice spring break, and see, we meet again on what, the 22nd, right? So we'll meet back on the 22nd. So I hope you can, I'm not sure if people can do much this spring break, but I hope you can at least relax and try to unwind a little bit. Okay. Have a nice break. I'll quit sharing now. Bye bye.